Meta unveils breakthrough research, decoding human thoughts into text with 80% accuracy in real time using non-invasive brain-computer interfaces. Date: February 14, 2025. Overview. Meta, formerly Facebook, has made groundbreaking strides in the field of brain-computer interface (BCI) technology. Their latest research reveals the capability to decode human thoughts into text with an impressive accuracy rate of 80% in real time using non-invasive methods. This pioneering work, conducted by Meta's Fundamental Artificial Intelligence Research Fair Lab in Paris in collaboration with the Basque Center on Cognition, Brain and Language, opens new avenues for understanding human communication and offers significant potential benefits for individuals with speech impairments. Key developments and findings. 1. Decoding brain signals. Meta's research has successfully demonstrated the ability to decode up to 80% of characters typed by participants through the use of magnetoencephalography (MEG) and electroencephalography (EG). These non-invasive techniques eliminate the need for surgical procedures, often associated with traditional BCI methods. The AI model developed, known as Brain 2 QWERTY, analyzes brain signals to reconstruct sentences based solely on typing activity from 35 healthy volunteers. 2. Understanding language production. The second aspect of the research explores how the brain translates abstract thoughts into structured language. Findings indicate that language production is hierarchical, beginning with general meanings and progressively refining them into specific motor actions such as typing individual letters. This research reveals that the brain employs a dynamic neural code capable of representing multiple layers of information simultaneously. 3. Clinical implications. The implications of this research are profound, particularly for individuals with speech impairments or brain injuries. Although promising, several challenges remain, including the requirement for participants to remain still in a magnetically shielded environment and the need for additional studies to assess the functionality in clinical populations. 4. Future directions. Meta envisions utilizing these insights to develop advanced machine intelligence (AMI) and apply them across various domains, including AI-driven speech assistance. Their commitment to open and reproducible science is underscored by a $2.2 million donation aimed at enhancing collaborative research efforts. Timeline of events. 2017, Meta, then Facebook, first announced its ambition to develop brain reading technology for typing via thoughts. February 2025, publication of 2 pivotal research papers detailing breakthroughs in decoding thoughts and understanding language production mechanisms. Common themes across sources. High accuracy of decoding. The 80% accuracy rate achieved in decoding brain signals is a significant milestone highlighted across multiple sources. Non-invasive techniques. The advantages of using non-invasive methods like MEG and EG are consistently emphasized as a breakthrough compared to invasive techniques. Potential for communication restoration. There is widespread recognition of the potential applications for restoring communication abilities in individuals who have lost the ability to speak, though practical challenges remain. Differences in perspectives. Emphasis on practicality. Some sources, such as MIT Technology Review, focus on the impracticality of current technology for real-world applications, while others highlight the theoretical implications and future potential. Technical details. Different sources provide varying levels of detail regarding the mechanics of the AI model and the nature of the neural processes involved in language production. Deep dive into the research. Decoding brain signals with Brain 2 QWERTY. Meta's AI model Brain 2 QWERTY operates by analyzing brain signals from healthy participants as they engage in typing tasks. The research utilized MEG and EEG technology, which records magnetic fields and electrical activities generated by neurons in real time. Participants typed sentences while their brain activity was monitored, allowing the model to learn the relationship between specific brain signals and the corresponding typed characters. The research team reported an average error rate of around 32%, indicating that while the system is not perfect, it marks the most accurate attempt at brain typing using a full alphabet keyboard to date. This level of accuracy showcases the potential for creating non-invasive BCIs that could assist those unable to communicate verbally. Investigating language production. In addition to decoding thoughts, Meta's research sheds light on the neural mechanisms that facilitate language production. By examining brain activity during typing, the researchers identified a hierarchical structure in how the brain processes language. This involves an initial abstract representation of a sentence, which is then broken down into word syllables and finally specific letters. The use of AI to interpret the MEG signals provided insights into this complex process, revealing how the brain maintains coherence across successive words and actions through a coordinated neural code. Implications for the future. The advancements presented by Meta could pave the way for revolutionary applications in both clinical and non-clinical settings. For individuals with speech impairments, non-invasive BCIs could offer a new means of communication, potentially restoring their ability to interact with the world. In addition, understanding the neural architecture of language production could influence the development of more sophisticated AI systems capable of human-like reasoning and communication. However, challenges remain before these technologies can be widely implemented. The current limitations include the requirement for specialized environments and the need for further research into the effectiveness of these methods in clinical populations. Conclusion. Meta's recent breakthroughs in brain-computer interface technology represent a significant leap forward in both neuroscience and artificial intelligence. By revealing the potential to decode human thoughts into text with notable accuracy and offering insights into the mechanisms of language production, this research could not only transform communication methods for individuals with disabilities but also enhance our understanding of human cognition. As Meta continues to explore these frontiers, the implications for both medical and technological advancements are profound, promising a future where communication barriers may be significantly reduced. Meta has recently revealed groundbreaking advancements in brain-computer interface BCI technology, showcasing its ability to decode human thoughts into text with up to 80% accuracy in real time through non-invasive methods. This research, undertaken by Meta's Fundamental Artificial Intelligence Research Fair Lab in Paris in collaboration with the Basque Center on Cognition, Brain and Language, signifies a substantial leap towards understanding human communication with significant implications for individuals with speech impairments. Key developments and findings. 1. Decoding brain signals. Meta's research illustrates that it can decode up to 80% of characters typed by participants using techniques such as magnetoencephalography (MEG) and electroencephalography (EG). This non-invasive approach eliminates the need for surgical procedures often associated with traditional BCI technologies. The AI model, named Brain2 QWERTY, decodes brain signals to reconstruct sentences based on typing activities from a group of 35 healthy volunteers. 2. Understanding language production. Another crucial aspect of the research investigates how the brain converts abstract thoughts into structured language. The findings suggest that language production is hierarchical, commencing with a general idea and gradually evolving into specific motor actions such as typing out letters. This understanding of the brain's dynamic neural code reveals its capacity to represent multiple layers of information concurrently. 3. Clinical implications. While the research shows promise for restoring communication in individuals with brain injuries or lesions, several challenges persist. These include the necessity for participants to remain still within a magnetically shielded environment and the requirement for further studies to evaluate efficacy in clinical populations. For her future directions, Meta envisions a long-term goal of achieving advanced machine intelligence (AMI) and applying these insights across various fields, including AI-powered speech assistants. The commitment to open and reproducible science is underscored by a $2.2 million donation to enhance collaborative research efforts. Timeline of events. 2017, initial announcement of Meta's then Facebook's ambition to develop brain-reading technology for typing via thoughts. February 2025, publication of two crucial research papers detailing breakthroughs in thought decoding and language production mechanisms. Common themes across sources. High accuracy of decoding. All sources stress the 80% accuracy rate achieved in decoding brain signals, marking a significant milestone in BCI technology. Non-invasive techniques. The use of non-invasive methods like MEG and EEG is consistently highlighted as a key advantage over invasive techniques. Potential for communication restoration. There is widespread acknowledgement of the potential applications for individuals who have lost the ability to communicate, although practical challenges remain. Differences in perspectives. Emphasis on practicality. Some sources, such as MIT Technology Review, emphasize the impracticality of current technology for real-world applications, while others focus more on the theoretical implications and future potential. Technical details. Various sources provide differing levels of detail regarding the mechanics of the AI model and the nature of the neural processes involved in language production. Counterintuitive information. 1. Impressive technology but limited practical application. While the ability to decode thoughts with 80% accuracy seems remarkable, the research is confined to controlled laboratory environments with significant limitations, such as the need for participants to remain completely still in a magnetically shielded room, which makes it impractical for everyday use or clinical settings at this stage. 2. Contradiction in progress and challenges. Although the advancements suggest a leap towards practical applications for communication restoration, the reality is that the technology remains largely theoretical, with significant barriers to real-world application. The high error rate, 32% errors as reported in decoding individual letters, indicates that while the system can reconstruct sentences, it still requires considerable refinement before it can be relied upon for accurate communication. 3. Dynamic neural code. The concept that the brain processes language hierarchically, starting from abstract concepts and evolving to specific actions, is intuitive. However, the notion that the brain holds multiple layers of information simultaneously challenges conventional beliefs about language processing, suggesting a more complex integrated approach to understanding human thought and communication. 4. Investment versus commercial viability. Despite Meta's substantial investment in research and development, the results thus far do not indicate a clear path to commercial viability. The technology is described as not being intended for product development, which contrasts sharply with typical expectations of such high levels of investment in tech research. In conclusion, while Meta's research represents a promising frontier at the intersection of neuroscience and artificial intelligence, the practical implications for real-world applications, especially in restoring communication for individuals with disabilities, remain limited and fraught with challenges. The insights gained into the dynamic processes of human thought and language offer a deeper understanding of cognitive neuroscience, but highlight the complexities involved in translating these findings into effective tools for communication. Meta's recent announcement regarding breakthroughs in brain-computer interface (BCI) technology has garnered attention primarily for its impressive claim of decoding human thoughts into text with 80% accuracy in real time through non-invasive methods. However, several critical aspects of the research are likely to be overlooked by many readers, yet they hold significant implications for both neuroscience and artificial intelligence. Below, I will identify these important elements and elaborate on their significance. 1. The importance of non-invasive techniques. While the use of non-invasive methods like magnetoencephalography (MEG) and electroencephalography (EEG is often highlighted, the implications of this approach are profound. Most existing BCI technologies require invasive procedures which pose significant risks and ethical concerns. Meta's non-invasive techniques not only enhance safety but also broaden the potential for widespread applications in clinical settings. The ability to decode thoughts without surgical intervention could lead to significant advancements in how we treat communication disorders, enabling more individuals to regain the ability to express themselves. Significance: non-invasive techniques can democratize access to BCI technologies, making them available to a wider range of patients, including those who may be too frail for surgery. Moreover, these advancements could help alleviate the stigma associated with invasive procedures, paving the way for acceptance of BCI technologies among both patients and healthcare providers. 2. Dynamic neural code. One of the research papers discusses the concept of a dynamic neural code that the brain employs during language production. This mechanism allows for the simultaneous representation of multiple layers of information, suggesting a more complex understanding of how thoughts are transformed into language than previously understood. The revelations about how the brain organizes and processes language may influence future AI developments, specifically in natural language processing (NLP). Significance: understanding the dynamic neural code provides insights into the hierarchical nature of language processing in humans. This knowledge could be instrumental in developing AI systems that mimic human thought processes more closely, potentially leading to machines that reason and communicate in ways that are far more nuanced and human-like. It opens up new avenues in AI development that transcend simple keyword recognition and instead focus on contextual understanding and generation. 3. Practical challenges and limitations. Despite the promising accuracy rates, the research also outlines significant challenges that remain. For instance, the requirement for participants to remain still within a magnetically shielded environment limits the practicality of the current setup. The need for such controlled conditions raises questions about how this technology can be utilized in real-world scenarios, especially for individuals who may have mobility issues or other physical constraints. Significance: addressing these practical challenges is crucial for the translation of research into clinical practice. Overlooking these limitations could lead to unrealistic expectations regarding the immediate applicability of the technology. Recognizing the hurdles involved encourages further research and innovation aimed at overcoming these obstacles, ensuring that developments in BCI are both groundbreaking and practical. 4. Future directions and ethical considerations. Meta's commitment to open and reproducible science is highlighted by their substantial financial support for collaborative research efforts. However, the ethical considerations surrounding brain data collection and the implications of mind-reading technology cannot be understated. As we advance toward a future where decoding thoughts becomes a reality, questions regarding consent, data privacy, and the potential misuse of such technology must be addressed. Significance: the ethical landscape surrounding BCI technologies is complex and requires careful navigation. Engaging with these ethical dilemmas early in the research and development process can help establish guidelines that protect individuals' rights and privacy. Moreover, this proactive approach can foster public trust in BCI technologies, ensuring that advancements serve humanity positively rather than creating new avenues for exploitation. 5. Long-term vision for advanced machine intelligence (AMI). Meta's long-term vision involves achieving advanced machine intelligence (AMI) informed by insights gained from human cognition. While the immediate focus is on decoding language and restoring communication for individuals with speech impairments, the broader implications for AI research are profound. The potential to leverage human cognitive principles could lead to the development of AI systems that not only learn from data but also reason and adapt in human-like ways. Significance: the pursuit of AMI marks a significant shift in AI research, moving towards systems that can interact with humans more naturally. This vision emphasizes the importance of understanding human cognition not just as a biological curiosity but as a critical framework for developing next-generation AI. The interplay between neuroscience and AI could yield technologies that augment human capabilities, enhancing productivity and creativity in unprecedented ways. 6. Collaborative research efforts. Meta's collaboration with the Basque Center on Cognition, Brain and Language and other institutions is an important aspect of this research. The interdisciplinary nature of this work underscores the necessity of merging expertise from neuroscience, artificial intelligence, and linguistics to tackle complex challenges. Significance: collaborative efforts can accelerate innovation by pooling resources and knowledge from diverse fields. This approach fosters an environment where breakthroughs can emerge as researchers challenge traditional boundaries and explore new ideas together. Such collaborations are essential for pushing the frontiers of knowledge and creating systems that are truly reflective of integrated human intelligence. 7. The role of AI in understanding human cognition. The research positions AI not only as a tool for practical applications but also as a means to gain deeper insights into human cognition itself. By studying how AI models interpret brain signals, researchers can refine their understanding of cognitive processes, potentially leading to new paradigms in both AI and neuroscience. Significance: understanding human cognition through the lens of AI could revolutionize educational practices, therapeutic approaches, and even social interactions. By developing AI that can better mirror human thought processes, we can create systems that enhance learning and communication, ultimately contributing to a more connected and informed society. Conclusion: Meta's advancements in brain-computer interface technology are indeed groundbreaking, but the nuances and broader implications of this research are equally important. From the ethical considerations surrounding mind-reading technologies to the potential for AI to enhance our understanding of human cognition, these aspects deserve attention and discussion. As we stand on the brink of what could be a revolutionary leap in both neuroscience and artificial intelligence, it is crucial to examine not just the achievements but also the challenges and responsibilities that come with such progress. The future of communication, interaction, and understanding may very well depend on how we navigate these complex issues in the years to come. 1. Decoding brain signals with high accuracy. Meta's breakthrough in brain-computer interface (BCI) technology, which allows for real-time decoding of human thoughts into text with an accuracy of up to 80%, represents a significant advancement in both neuroscience and artificial intelligence. The use of non-invasive techniques like magnetoencephalography (MEG) and electroencephalography (EG) is particularly noteworthy, as these methods avoid the surgical risks associated with traditional invasive techniques. This not only enhances the safety of the technology but also increases its potential applicability for individuals with speech impairments or neurological conditions. 2. Understanding language production mechanisms. The research sheds light on how the brain processes language, highlighting a hierarchical and dynamic neural coding structure that underpins language production. The ability to identify how abstract thoughts are translated into structured language via neural mechanisms provides crucial insights into cognitive neuroscience. This understanding could inform the development of more sophisticated AI systems that mimic human thought and language processing, potentially leading to advancements in natural language processing technologies. 3. Clinical implications and challenges. While the research holds great promise for restoring communication abilities in individuals with brain injuries or conditions that impair speech, practical challenges remain. The requirement for participants to remain still in a magnetically shielded environment limits immediate clinical applications. Furthermore, the current error rate of 32% in decoding characters indicates that while the technology is impressive, it still requires refinement before it can be reliably used in real-world settings, particularly for patients with varying degrees of cognitive and physical capabilities. For future directions and open science commitment, Meta's long-term vision includes the pursuit of advanced machine intelligence (AMI) and fostering collaboration in the scientific community. Their commitment to open and reproducible science, underscored by a $2.2 million donation to support collaborative research, emphasizes the importance of shared knowledge in driving innovation. This approach not only enhances the credibility of the research but also encourages further exploration of the implications of BCI technology in various fields, potentially leading to breakthroughs that can significantly improve quality of life for individuals with communication challenges. 1. The case of brain-machine interfaces in ALS patients. In recent years, significant advancements have been made in brain-machine interfaces (BMIs) for patients with amyotrophic lateral sclerosis (ALS), a neurodegenerative disease that can impair speech and mobility. Notably, researchers at the University of California, San Francisco developed a system that enables ALS patients to communicate using a brain implant. This system uses electrodes implanted in the brain to decode neural signals associated with speech, allowing patients to type words on a screen at a rate of up to 62 words per minute, significantly enhancing their ability to communicate. Similar to Meta's recent breakthroughs, this case highlights the potential of advanced neural decoding technologies to restore lost communication abilities. 2. The BrainGate Project. The BrainGate Project, a collaboration between various universities and research institutions, has been working on developing invasive brain-computer interfaces for individuals with paralysis. This project aims to restore movement and communication abilities by decoding brain signals and translating them into actionable commands for external devices. In one notable trial, a participant with spinal cord injury was able to control a robotic arm using only their thoughts, demonstrating how advanced neural interfaces can provide new avenues for interaction with the world. This parallels Meta's efforts in non-invasive brain-computer interfaces, both striving to bridge the gap between thought and action. 3. Neuralink's brain interface technology, founded by Elon Musk. Neuralink focuses on developing implantable brain-machine interfaces to enhance cognitive abilities and address neurological disorders. Neuralink has conducted experiments where pigs and monkeys were fitted with devices that allowed them to control computers or robotic limbs using their thoughts. This research shares similarities with Meta's work, particularly in understanding how thoughts are translated into actions. While Neuralink employs invasive techniques to achieve high fidelity in signal decoding, Meta's recent breakthroughs highlight advancements in non-invasive methods, underscoring the ongoing exploration of how technology can interface with human cognition. Meta's recent advancements in brain-computer interface (BCI) technology, particularly its ability to decode human thoughts into text, promise to reshape the landscape of communication and artificial intelligence. With a reported 80% accuracy rate in real-time decoding through non-invasive methods. This breakthrough not only opens new avenues for those with speech impairments but also offers profound implications for our understanding of language processing and cognition. Future predictions. 1. Enhanced communication aids. As Meta continues to refine its BCI technology, we can anticipate the emergence of sophisticated communication devices designed for individuals with speech limitations due to conditions such as ALS or strokes. These devices could facilitate more natural interactions, allowing users to communicate their thoughts in real time without the need for physical speech, thus significantly improving quality of life. 2. Integration into everyday technology. The advancements in BCI could lead to the development of consumer-friendly applications. Imagine typing on your smartphone or computer simply by thinking about what you want to write. While the current technology requires a controlled environment, future iterations may become more portable and accessible, ultimately being integrated into everyday devices, making communication more fluid and intuitive. 3. Research and collaboration growth. Meta has committed to open science and collaborative research. This approach is likely to accelerate advancements in neuroscience and AI, fostering partnerships with universities and research institutions globally. Such collaborations could lead to rapid innovations in understanding brain function and developing new applications for BCI technology. 4. Understanding cognitive processes. The insights gained from this research regarding how the brain transforms thoughts into structured language could revolutionize our understanding of cognitive processes. This might lead to improved educational tools that cater to how the brain naturally learns and processes information, potentially enhancing learning outcomes in various educational settings. 5. The ethical and privacy considerations. As BCI technologies advance, ethical concerns surrounding privacy and consent will come to the forefront. The ability to decode thoughts raises significant questions about mental privacy. Future frameworks will need to address these ethical dilemmas to ensure that individuals' rights are protected as BCI technologies become more widespread. 6. Mental health applications. The ability to decode thoughts and emotions could pave the way for new mental health interventions. Therapists might leverage BCI technology to gain insights into patients' unexpressed feelings or thoughts, leading to more personalized and effective treatment plans. This could revolutionize how mental health is approached, moving towards more data-driven interventions. 7. Improved AI models. The research into the neural mechanisms of language production will likely inform the development of more advanced AI systems that better understand and generate human language. This could enhance natural language processing applications, from virtual assistants to advanced chatbots, making them more effective and human-like in their interactions. 8. Regulatory frameworks. As the technology matures, regulatory bodies will need to establish guidelines to manage BCI applications, particularly in medical settings. Ensuring the safety and efficacy of these technologies will be crucial for their acceptance and integration into clinical practices. 9. Increased accessibility. As the technology becomes more refined, we can expect efforts to ensure that BCI devices are accessible to a broader range of users, including those in low-resource settings. This could involve creating cost-effective solutions that cater to underserved populations, promoting health equity. 10. Long-term research in neural architecture. Meta's pursuit of understanding the principles of human intelligence could lead to groundbreaking discoveries about how the brain works, which in turn could inform not only AI development but also advancements in various scientific fields, including psychology and cognitive neuroscience. Conclusion. Meta's breakthrough in decoding human thoughts into text marks a significant milestone in the integration of neuroscience and artificial intelligence. The future holds immense potential for enhancing communication, advancing AI technologies, and improving the quality of life for individuals with speech impairments. However, as we venture into this uncharted territory, careful consideration of ethical implications and the establishment of regulatory frameworks will be essential to guide the responsible development of these transformative technologies. Through continued research, collaboration, and innovation, we may soon witness a new era of human-computer interaction that bridges the gap between thought and expression.